In the previous two lectures on introduction to tensors, we first got introduced to the idea of tensors, and then we looked at how scalars, vectors, which we are already familiar with, and tensors, which we will use quite a lot in rheology, how are they related. And we also started looking at some of the operations, and the overall framework that we are following in terms of looking at description of vector and tensor quantities is in terms of three different notations. So we use boldface notation if we want compact and for understanding physical significance, and of course, this is not expressed for a specific coordinate system. When we use index notation, it is compact and it is easy for manipulating terms and equations and simplifying equations and so on, and these are generally expressed only in Cartesian coordinates. Of course, the complete governing equations is what we need if we really attempt a solution for a given problem, either computationally or analytically, and since these are complete governing equations, they are fairly lengthy and also expressed in a specific coordinate system of interest. So, in this lecture we are only looking at index notation and how it corresponds to a specific boldface notation. So, we already saw that the base vectors which are specific to certain coordinate system, how we actually use them using index notation. So, where I and j are the dummy indices, and so just to summarize the kind of the operations that we had seen how a dot product of two vectors or a scalar product of two vectors or the curl or the cross product of two vectors, how are they expressed. And so, now in today's lecture we will look at how some of these operations are carried out for tensors. And to begin with, we will look at multiplication of a scalar and a tensor. And this is again just to see, for example, this is a tensor which we will use quite often, and so this is the boldface notation, and again to remind you that two under bars indicate that this is a tensor, and of course, this is specifically the unit tensor. And so, this in index notation would be expressed as P delta ij E I E j, because the dyads are used for indicating. And so, in index notation really we would just if this term is there P delta ij, that implies that we are talking about 9 components, because I and j both can take values of 1, 2, 3, but we are only talking about the components where delta ij is 1 having that value minus delta p. So, basically for when I is equal to 1 and j is equal to 1, or similarly I is equal to 1, j is equal to, and so on, for these values we will get component p, and for all other values of I and j we will get 0. So, basically this is as expected, what we are expressing here is this in matrix notation, this is how we would explain it. So, therefore, we have a unit tensor which is being multiplied. So, in simply the unit tensor in index notation is this. Using Kronecker delta. So, now what we will do is look at the next operation. Addition and subtraction of two tensors is again can be expressed. So, if we have, let us say, sigma minus tau, and mind you, actually if this sigma is the total stress and tau is the deviatoric stress, then this difference is nothing but minus p times I. But in index notation this can be written as sigma m n minus tau m n, and we are keeping the same index here because we know that when sigma 1 1 has to be subtracted from tau 1 1. So, therefore, whenever we see a term like this we know this is a tensorial equation with 9 components, and both m and n have to go from 1 to 3. So, in such cases it is completely incorrect to write this, because when we write something like this, m and n and I and j can take independent values, and therefore, this is not really permitted. So, we could also write the same thing this as sigma I j minus tau I j. So, these two are completely equivalent, and just to remind you, that is why we call these indices m, n, I and j as dummy indices. So, that is as far as addition or subtraction of two tensors is concerned. Now, let us look at scalar or double dot product of two tensors. Such operations are fairly important in rheology, for example, when we look at viscous dissipation. Because of viscous nature of complex materials, whenever we impose deformation rate or a strain rate on the material, viscous dissipation is actually nothing but stress into strain rate. And clearly these are tensor quantities, while this is a energy measure. So, therefore, it is a scalar. So, the double dot product of stress and strain rate will actually give us viscous dissipation, which is a scalar. Similarly, the strain energy, which is again a scalar, and this is related to stress and strain, stress multiplied by strain. And for one dimensional situation, of course, both of these just multiply each other, but we know in general that they are tensor quantities. So, therefore, again the double dot product of stress and strain will give us strain energy. So, let us just look at that. If stress is denoted by sigma and strain by E, then we are interested in finding out the strain energy, which is defined as this in boldface notation. So, how is this represented in index notation? So, again we can use what we have been doing, represent sigma as in index notation, and then this is double dot product with E, and this is with E m E n. So, now given that there are two dot products, what we have is a dot product between these two and a dot product between these two. So, we know that E dot q dot E dot m is going to be delta q m, and similarly E dot p dot E dot n is going to be delta p n. So, therefore, we can write this result as sigma p q E m n delta q m and delta p n. And clearly, because of these Kronecker delta, q and m have to have the same value, and similarly p and n have to have the same value. Therefore, this can be written as sigma p q E q p. Alternately, we could also write this as sigma n m into E m n. And so, you can see that this is a scalar quantity, and both n and m are repeated, or p and q are repeated. So, this is a sum, and just to write it out to make ourselves familiar, since both p and q or m and n they vary from 1 to 3, what we are writing here is sigma double dot E is actually equal to sigma 1 1 E 1 1 plus sigma 1 2 E 2 1 plus sigma 1 3 E 3 1 plus sigma 2 1 E 1 2 and so on. So, you can see that there are going to be 9 such terms which will sum and give us the result, which is the scalar product. So, this is called scalar product of two tensor, or it is also called the double dot product. So, that is another operation which is useful whenever two tensors are involved and the resulting quantity is a scalar quantity. Now, let us look at a dot product of a tensor and a vector. And again this is very important when we have to talk about contact forces in continuum mechanics. The contact forces, which are forces acting on a surface, it is between in a material. If we have a hypothetical surface and the two parts of the material will exchange this contact force. So, each contact force is associated since it is a force, it is a direction, but it also acts on a surface. So, any such surface we will have the contact force T, and then of course, at that point the surface unit normal is n. So, to find out this T, we actually need to know the stress tensor, and therefore, a single dot product of tensor and a vector gives us another vector. So, given that in our course we are dealing with mostly fluids which have no polar ordering, and therefore, we have seen that sigma is equal to sigma t, or in index notation we can write this as sigma mn equal to sigma nm. So, let us look at the dot product of the stress tensor with a unit normal vector, and again we can write this in index notation as sigma ij ei. So, again we represent and then this is multiplying with. So, as we can see these two will undergo the dot product, and therefore, we know that E dot E k can be represented as delta j k. Therefore, this result can be written as sigma I j into n k into delta j k into E I. So, what we have therefore, in effect is a vector quantity, just the way a unit normal vector was represented using one set of base vectors, tensor was represented using a dyad. We have the overall resultant of a tensor product with this vector as a vector quantity, and we can use now the property of Kronecker delta to say that j and k have to be identical. So, therefore, this could be written as n j E I. So, many times what we will do is we will not be writing this kind of the notation to indicate the base vector. So, we will just indicate this as sigma I j n j. Given that j is repeated, this implies that each ith component. So, I implies the component, and therefore, this is a vector quantity, and j implies summation. So, just as an exercise to think about, if we have let us say a product like this, what are we implying here? M is the component. So, both this is also a vector, this is also a vector. So, therefore, we have mth component of the two vectors, and this is simple vector addition. The first component will be summed with another first component and so on. And since there are n is repeated in this, n will be actually summed over. And so, if I were to write let us say the second component of this equation, what I am saying is m is equal to 2. So, therefore, then what I need to write is a 2 n v n plus a 2, and since this is n is repeated, the complete writing of this would be a 2 1 v 1 plus a 2 2 v 2 plus a 2 3 v 3 plus a 2. So, therefore, this is a whole first vector, this is the second vector, and this is what is the advantage with index notation. You can see that these three terms are written very compact way using this, and since we know the notation framework, we know that since n is repeated, it has to be summed over, and we are talking about mth component of this tensor, of this vector. So, now we have looked at operations which are related to the getting a scalar from two tensors and then getting a vector from a product of tensor and a vector. The last product that we will see is where the two tensors are involved. So, if we have let us say two tensors A dot B, then the resultant is a tensor again, and again we can write this as A P Q E P E Q and dotted with B M N, or let us just use I J, because I have kept on highlighting that these are dummy indices and we could use any possible indices. And so, again like in the earlier case there is only one dot product and these two would be involved, and if we are getting familiar with this, then we can quickly see that Q and I have to be same, because this dot product is nothing but delta Q I, and therefore, I can directly write this as A P Q B Q J E P E J. In fact, I need not write the two unit vectors also, because I know by looking at this quantity that Q is repeated. So, there is sum over it, sum over Q, and we are talking, when I write this is a P j component. So, if I am interested in let us say this A equal to B is a tensor M, and let us say I am interested in writing down M32, and clearly the P j component is what we have written here. So, by this we imply that P is equal to 3 and J is equal to 2. So, using this I can write M32 is equal to A 3Q B Q2, and since Q summation is involved, this will completely write as A31 B12 plus A32 B22 plus A33 B32. So, again a sum like this is compactly written using the index notation. So, what we have seen is any of these operations when we discuss in rheology, many of these quantities we will be using, and at that point we will pay more attention to the physical significance of these quantities, but it will be handy, it will be very useful for us if we are able to quickly see the correspondence between the index notation and the boldface notation. And for any work in this area, this is one of the skills that is very essential in terms of doing manipulations of equations and simplifying governing equations. So, the next set of operations that we will summarize are related to derivative operations, because all the things we have seen so far are additive or dot products and cross products, and so each of these have a very important physical significance. And of course, in rheology we will also have time as well as space derivatives. So, what we will do is quickly look at some of the derivatives and operations which are related to that, how we will use them. For example, let us say time derivatives are relatively easy to talk about in terms of index notation. If we have let us say a quantity sigma, which is the stress tensor let us say, and we are interested in stress derivative with time, partial stress. So, that of course, in boldface notation we will write as del sigma by del t, and clearly this is a tensor form, because each and every term of sigma is going to get the partial derivative. So, what we imply here is, if there is a sigma 2 and we are writing del by del t, we basically have if let us say all the other terms are 0, then this implies that there is only one component which is non-zero, which is del sigma 2 by del t. If all the 9 components are non-zero, then we will have 9 such derivatives. So, therefore, in boldface notation we write it like this, and in index notation again it is simply written as del sigma I j by del t. So, as soon as we see 2 indices and a partial derivative of this, we know that this is a tensor equation, which means that there are 9 components of this equation. The deviatoric stress that we talked about, for example, is indicated by tau. Its derivative in index notation will be del tau I j by del t. And the Maxwell model that we will discuss quite a lot is nothing but tau I j plus lambda times del tau I j by del t is equal to eta times gamma dot I j. So, we can see that this is 3 dimensional Maxwell model, because there are 9 components of stress, 9 components of strain rate and 9 components of the derivative. And of course, if we were to write let us say the simple shear, in simple shear what we will see quite often is only the off diagonal elements will be non-zero, and in simple shear only one of those off diagonal elements will be non-zero, and for the time being let us say that I is equal to 1 and j is equal to 2, or j is equal to 1 and I is equal to 2. Because of symmetry both of these will be same, and so then in that case the equation will reduce to lambda del tau 1 2 by del t is equal to eta gamma dot 1 2. So, therefore, in index notation when we write, we imply all the 9, and quite often for a simple situation when there is only 1 or 2 components non-zero, then we will write them in more detail. So, as I have said earlier, we will indicate the boldface notation like this. We will indicate the index notation, and if we want to solve, then this is the complete equation. So, just to complete the picture, let me also maybe just write the Maxwell model in boldface notation itself. So, that will be del tau by del t is equal to eta gamma dot, or more correctly, because gamma dot is related to, in our course, the strain tensor as D. So, therefore, we can this is the boldface notation. This is the boldface. So, now let us look at some of the other operations, because with time derivatives it is relatively simple, because time itself is a scalar. We have other spatial operators, for example gradients and divergences. So, here we have the first quantity which is gradient of a scalar. So, in this case let us say rho is a scalar, and its gradient is written as gradient of rho in boldface notation. This is a boldface notation because we know this is a vector quantity, this is a vector quantity. So, using index notation we write this as del rho by del xi. We write xi in rectangular coordinate, this will be x y z. Coordinates, it will be x y z. Similarly, it will be r theta z in cylindrical coordinates, and so on. So, generally we are saying that these are the 3 coordinates for our 3 dimensional space. So, to write this more generically, we write x1, x2 and x3, implying the 3 different directions. So, therefore, a position vector will be nothing but let us say xm. when we write xm, we imply this is a position vector, and of course, we know that this is equal to x1 e1 plus x2 e2 plus x3 e3. So, therefore, this is used the position vector and the derivatives with respect to coordinates, we use the symbol xi. And so, whenever we write del rho I by del xi, this is a vector quantity and it is the gradient of rho. And in this notation, it is clear that this, when we write, we are saying del rho by del x1 E1 plus del rho by del x2 E2 plus del rho by del x3 E3. And now I hope you can see that what do we mean when we say that in index notation we are only trying to indicate Cartesian coordinates, because if this were to be a cylindrical coordinate system, then we will have terms like this where it is 1 over del rho by del theta E theta. So, there will be terms like this which are not really being represented in index notation. So, they do not really come in index notation, and therefore, the index notation is predominantly is only for the Cartesian coordinates. So, the way we imply and understand the index notation is not that it is only valid for Cartesian coordinate, but we understand how it is written. For example, if you have a heat flux vector which is written as conductivity times gradient of temperature. So, this is the bold face notation, and of course, it does not have any significant reference to any specific coordinate system. But now, if I were to write this in index notation, what I will write is qk is equal to minus k del t by del x k. Since I use conductivity also as k, maybe that is not the best choice for index, and so as it is a dummy index I can use any other. So, let me use I. So, qi is minus k del t by del xi. So, as soon as we write this, we can see that the terms which are similar to what we had said in terms of cylindrical coordinates are not included, but as soon as I see this kind of an equation which is including in index notation, I should immediately think that this is corresponding to this boldface notation. So, when I expand this in cylindrical coordinates, I should automatically write the overall governing equation correctly. So, if I see this equation for example, in terms of as I said q I is equal to minus k delta t by del xi. When I write this for cylindrical coordinates, I first have to understand that this is gradient of t, and then I have to apply the cylindrical coordinate or any other curvilinear coordinate gradient operator. And that is why the index notation is only a notation to write down equation in a compact fashion. It is not, because Cartesian coordinates are simple, we are using Cartesian coordinate as in index notation, but it does not imply that the equations written in index notation are only useful for Cartesian coordinates only. So, now let us go down and look at the other operation, for example, divergence of velocity. This is something which will be very useful in most of fluid mechanical calculations, and of course, we also know that this is 0 for incompressible fluid, and again we know that this quantity is a scalar. And just to again go through the operation, what we have is del xi ei and dotted with vk ek, and again because of the dot product between I and k, we know that we can use Kronecker delta to imply del I k, and since I and k have to be same, we can write this as del v by del x k, or alternately del v I by del x I. So, any time in a governing equation I see a term like del v m by del x m, I should be able to immediately say that this is nothing but divergence of velocity. Because both of these repeated, again we know that overall this quantity is going to be del x 1 plus del v 2 by del x 2 plus del v 3 by del x 3. So, this is as far as the divergence of velocity is concerned. For the course on rheology, the gradient of velocity will be very important, and here there is possibility of multiple interpretations or multiple notations. So, in our course we will follow this particular notation to indicate the velocity gradient. In other notations alternately, it is also possible to write this as del v j by del x I, implying, and in this particular course we will not use this, we will only use this definition. And so, the final operation which is very useful in case of linear momentum balance is divergence of sigma, and so here for example again del by del x k of E k dotted with sigma m n E m E n, and again I will do this quickly, hoping that some of you are now getting familiar with what we are trying to do. So, k and m have to be the same. So, therefore, this can be immediately written as del x k sigma k n, and since k is being repeated, there is a sum over it, and this is the vector. It is a vector because n is the only quantity which is operational here. So, therefore, nth component of the divergence of stress will be involved in the nth component of linear momentum balance. And so, with this we have now looked at several operations. In the first lecture we tried to get familiarity with the concept of tensors. In the second lecture we looked at some of the operations which involved scalars and vectors, and in this lecture we looked at operations which involve tensors and other quantities, as well as some of the important time and space derivatives. So, with this now we have the overall machinery to indicate any to write down any governing equation which is involved in rheological analysis.